Hello everyone, here I am Vadhel Sagar. Let us continue our discussion regarding the electric charge and field. Part number 7. Welcome to all. Okay, so at last in the part number 6 we discussed about the electric field lines, and that topic is not completed in that part because of the lack of time. That we have to continue here, and this slide is already we discussed about these things. So let me retry let me again explain these things what actually the electric field lines, it is a pictorial diagram or the representations of the electric field with the help of lines, that is named as electric field lines. It is a vector pointing of the directions of electric field. So electric field line shows directions of the electric field that we already seen earlier. It was positive charge is radially outward electric field and negative charge is radially inward electric field. So that is what inward and outward, it has a direction, and direction has only vector quantities. So that is nothing but the electric field, it is a vector quantity that we already discussed. Okay, this is a more complex diagrams, and that we ended something in this discussions. So yes, there, according the electric field strength, we have to understand what way you can understand. So okay, here at the O point, if you have don't see these things, I will explain what I am right here. That may be already discussed in the part number 6, but still try to try to connect them, what today's discussion, what yesterday's discussion. Okay, so what, okay, if it is your point charge is on O point, then this, suppose it's all electric field lines are radially outward, suppose, then what the way you can judge the electric field strength? It means what the parameter through we can judge our electric field is strong or weak. So there one parameter we thought about the electric field lines, that electric field lines is more, then its electric field is strength more strong. If it is less in number, then it will be weak in continue. Okay, that is not enough the way of judgment. That's why we go for the relative density of the field lines, that is named as, it is not here maybe, but that we are seeing that electric field strength, it is called relative density, and that is called flux of the system. So as you can see here, this R area and S area, both the one rectangle we are taking, suppose you can think about it, one card you have in this much size. Once this card you are putting at the R position, and the second time you are putting at the S positions. Now when the R position is nearer to the charge and S position is outward, it means little bit more far than the charges. Then when you are on R, near to the R, near to the point charge on R position, the number of field lines passes through the card area, it is some number, it is finite numbers. Now the same direction, we are not changing the direction, we are just shifting this, we are going far away from this position. Then it is, you are kept your position is S, the number of field lines passes through the that same area which is less. It means that per unit area, the number of field lines associating with that particular area is reduces as we go away from the system. That is written here, and that we already discussed. What is new today? To understand the dependency of the field lines on area, that we already dependency on area, we've seen that, because at R position, at S positions, area dependence, number of, if area constant, then the field lines is reduced. If you want, don't change the number of field lines, you have to increase your area. Okay, suppose the R is associating with the three field lines. But in this position, if you want still three lines, then your area should be these, and this much larger. So your area should be changes. In this same concept, what I'm trying to explain, it is represented in the P1 and P2 area. The P1 area, you can able to see that how many field lines total you can calculate. If you are go far than the point charge as a P2 size, P2 positions, then the size of the P1 and P2, think about it. But the number of field lines associated with these two areas, P1 and P2, which is same. Why it can be same? Because you are increase your area if you go far than the point charge. So the two way you can play, either kept your area fixed, then your field line will change. If you want to fix your field line number, this number of field lines is number fixed, then you have to change your area. So trying to understand here what I have to trying to explain you, to understand the dependency of the field lines on the area. Yes, it is depends, but how, or rather the solid angle subtended by the area element. Now you can go back to your 11th class and the referred solid angle. Solid angle, it means you are in not a 2D case. It means you are in the plane, you have simple theta. But when you are in the 3D, you have a particular cone. You are seeing that ice cream cone. So that ice cream cone has not a 2D angle, it has a cone that is your solid angle. So trying to see that inside the point, the cone has a point. This is a one cone you are trying to see. It is a one cone. That cone has one angle, that is called solid angle. You are you construct, you are trying to see, this is the top of the cone and this is one cone, this is called solid angle, that is your d omega is represented already. So trying to understand solid angle things, it is solid area is considering by the angle, solid angle. Angle is defined in a two dimension. Delta theta is equal to delta L by R, that is a very common to us. That is, if you are just multiplying here delta L element that we seen now, this and this, so this is your delta L, this is your delta theta, and this is your R, then if you can able to write this. But the same thing if you want to write in the three-dimensional case, so there this exactly these things we done in the 11th class. You can go to that class, which chapter I forgot, but it is exactly steradian and radian at the top of the book it is mentioned. Okay, this is a solid angle, this is a 2D angle, this is a 3D angle. This is called delta omega is a solid angle. Solid angle, it is having a delta S by R square. Here your length considering, here the delta S is your plane area, because it now it has area element. Trying to see these things, it is representing here. This is a trying to see, this is why you face a difficulty, because this is a 2D picture and we have to understand in 3D system. So trying to keep with the ice cream cone, this is your ice cream cone placing, and this is your cone structure. So that is your where ice cream you are putting on the top of the, that area is your plane area delta S. Inside this is your R, and this is your solid angle d omega. So the d omega is equal to, or delta omega is equal to delta S by R square. Okay, okay, go ahead. The element of area subtending by the solid angle at position P1, how much area is covered by the P1 part, you are trying to see that. Okay, so if you want to find delta S, it should be multiplied with the R square multiplied with the solid angle. Okay, so here we are just finding the area element R square multiplied by solid angle. At the particular P1 position, what is R? R1. Then your R1 square delta omega. Subtend area element subtending by the solid angle at P2, it's R2 square delta omega. Now give me the answer where solid, where area element is more, at P1 or P2. Very simple, as you can able to see in figure also, the area at P1 is less than the at P2. Why? Because also here the R1 and R2 trying to see. R2 is more, so this number is going to be more, so area element more, and this is visible also. So very easy to understand. Okay, this how you bring you can able to understand. Here we are trying to see that area element. If you want to see the area, plane area, then r square should be multiplied. Okay, so this is your r square multiplied by d omega. Okay, we are proceeding ahead. The number of lines cutting that area element are the same. The number of field, see area is less, but still the number of field lines passes is the some number. Area is more, still the number of field lines passes through the area is same. So something is mismatching, but the something is same. What something is same? Number of field lines associated with it is same. So I can compare this something number, which is the number of field lines per unit area. So the n divided by that is n is your number of field lines. We don't know here we have finite drawing, but in this some case, specific case n number of field lines can be passed. So n divided by this area element, n divided by the that area elements, because the field lines is same. So I can equate it. You can place your equalize sign here, then n can cancel out, d omega cancel out. So I can say number of field lines associated with the area element is depends upon the 1 upon r, 1 upon r square. So this is tells us at the end all about the dependency of the distance from the point charge. So the strength of the field clearly at the end has 1 upon r square dependency. As your r is decreases, then your field is increases, strength is increases. As your r is increases, it is in the inverse relationship, so the field strength is decreases. Clear statement here. Okay, now we enhance our discussions in a way of point charge. This is a pure theoretical discussions here. Today may be bored you are because you you don't because the electric field concept, it is a little bit imaginary concept. So you have to think about it. You have to made a picture of in your brain, and I'm trying to give the maximum what it exactly mean of electric field. The picture of field lines was first time invented by the Faraday to develop the intensive non-mathematical way. This is not a mathematical tool, is visualizing the electric field. Why we are taking the electric field line concept in our physics? Because of we have to visualize, we have to see something, because it is not existing. It is exist, but it is not a visualizable thing. So for the visualizing point of view, we made electric field line concept around the charge configuration, that the Faraday called it is a line of force at that time, at those time. This term is somewhat misleading, especially in a case of magnetic field. The more appropriate term is field line. You can't say it is a line of force. It is after that it named as field lines. It is a electric field lines, magnetic field line. That way you can adopt it, and that's why we are in our book also we named as electric field lines instead of electric line of force. Okay. Electric field lines are thus a way of pictorial mapping of electric field around the configurations of charge. So electric field lines is nothing but the just mapping system. We are mapping something through which we can judge our electric field. An electric field is the tangent to its point, is the directions of the net field at the point. Okay. Now suppose at this position, particular at this point, I want to find that what is exactly electric field direction. So at that point you have to take a tangent of this particular curve. So if in this point you have to take curve tangent, then it is this is the direction. So this is the directions of electric point of electric field in this position, which is nothing but the tangent to that curve at that point. It is mentioned here. An arrow of the curve shows the directions of electric field. This is all about the basics of electric field. You how to take it. So here the one, oh, that is that still left to explain these things what is. So here the plus charge, here also plus charge, the two similar charge is always repelling each other. So the diagrams, the electric field lines also has a nature of repulsive natures. You can trying to see that because are both are emerging outward, because both are positive charge. So the both charges are the having electric field, and that is the lines are emerging outward. So they both are emerging outward, and it has some specific the way of electric field. Okay, but they are not attracting each other, so both are repelling each other. One flow in this direction, one is flow these directions. Okay, so this is a more general view of its positive charge. If it is single charges of, if you have, there is no other charges around the system, then only single charge this electric field can be. Likewise, if it is positive, outward; if it is negative, then inward. If it is two positive charge, that we already seen, if the system of charge and there is a two charge, one positive and one negative, they attract each other and they make one loop of electric field. This charge is generating, it is generating means source charge, because it's a outward, and this negative charge is taking inward, so it's accepting. So they make a one loop. This way it's also going, the due to the picture scenario, this go and then it is accept also. So this is the system of one plus charge and one negative charge. This one make a one system. System is always named as when you have one or more than two part. So here we have a two charge, so we named as one system, and that system is named as dipole because it has two pole, so it's named as di, and pole means parts. What is the mean of parts? Chedo, that is a two, that's why it's dipole. So it is has two pole, which has one positive, one negative. Let us go for the more in detail of this dipole. The two equal and opposite charges q and minus q are a dipole named shows a mutual attractions between the charges, because both are opposite charge and opposite charges always attract each other. The field lines follow some proper important general properties. Field lines start from the negative charge, as we seen in this, because it's emerging outward, and is end up with the negative charge. That's a very general thing. In charge free region, wherever you are found out the charge free region, because charge is not there everywhere. Particular two places only there is a charge is existing. In the charge-free region, electric field line can be taken to be continuous curve without any break. If you are trying to see that anywhere else, the field lines are continuous. Here I am showing that break, but actually it is not break. So it is a curved outwardly and inwardly it is accepting. So this is a continuous. It should be. Two field lines can never cross each other. That is also you can able to see in this picture. The two field lines, this is all basic scenario also we seen in the, sorry, also we seen in the magnetic field lines characteristics, but this is also applicable here also. There we have a n pole and s pole, here the positive charge and negative charge, the same magnetic field lines structure or the scenario you can applicable here also in the electric field line concept. The two field line can never cross each other. Electrostatic field lines do not form any closed loop. This follows the conservation's nature of the electric field line. No need to be exactly, it should be in the one loop. That is one more thing you have to accept in the ad. Thank you very much. If any kind of difficulty you face during this our discussions is, you can mention in comment bar, and you are satisfying with this style what we are proceeding from the last few weeks, so then also comment it. If you want any kind of change also, then you can mention any query, any type of suggestions. If you are trying share, you can. Thank you very much.